каждый раз считаем. То есть, другими словами, вы считаете, сколько раз у вас выпал орел. Вы говорите, что ваше это множество здесь, это множество выпадения орлов. Соответственно, каждый раз, когда орел выпадает, ваш счетчик сдвигается на единичку. Значит, вот эта случайная величина равна количеству орлов в последовательности длины n. Вот. Так, интересно, Саша уже можно его забирать? Саша, а можно брать уже, да, микрофон? Ладно. Можно брать его? Да. Угу. Спасибо. Okay. So first, let us make this intellectual computation. Maybe I will enumerate them, and this will be theorem 1, this is theorem 2, and this is theorem 3. And theorem 3 is our life goal for the first half of the lecture, so let's prove. Theorem 2. The proof so we consider our nu, which is the sum of psi e. So we know that then the mathematical expectation of nu should be the sum of mathematical expectations of this psi e. The sum is finite. I'm not doing anything complicated, okay? So this is a linear thing, and we are very fair. Now we can say, what is this? As Daniel asked us, so we will try to investigate. So this is the same thing as to say that we sum up the probabilities that our event entered the set B, because the value of this function is always 1 or 0, right? So we have to multiply the value on the probability. That was our simple definition of the mathematical expectation, and so that's what we did here. Okay, great. So we sum up all the entrances to B. Then, in other words, it's the same thing as to sum up the probability of B. And so we sum up from I to N, and we know that the probability to enter B is always P. So this is nothing else but NP, right? So now, what about the variance? The variance can be slightly more delicate, but not much. So we will compute it like here. Variance, it's a mathematical expectation of the difference between our random variable and its mathematical expectation squared, right? So now we can remember again what was a random variable we have. So we can say that we consider here something like that. And now, because you understand what happened. We said that this guy is a sum of the characteristic functions, and this n can be considered as a sum of np. So instead of writing n here, we wrote n the sum here, because it's a constant from I to n. Clear? Great. So then we can compute this square, because we know how to do that, and we say that these are the differences between this person and these are the x, so g minus p, right? So what do we know additionally? We know that actually if we had a function he, if we consider a square of this function, It's just the same function as our function itself, because it has only two values, 1 and 0, right? So they just coincide. So we can continue to study this person. And we can say that apparently, here we can write it as a mathematical expectation of our random variable itself, because they coincide, so we can replace it, minus 2pe of the same person plus p squared. Right? But this we can compute already, because we were smart enough to do it here, so we know who they are, and thus we can say that we can use this knowledge and say that we deal with np minus p squared. Because there is a p here, so p here, so p minus 2p squared plus p squared. This is what we have here. So this is exactly np 1 minus p. So now the goal is to investigate what happens here. But this is very simple, because we can use symmetry. We can say that if I and j are different, then this complicated guy can be simplified. We can say that we have a product here, minus p, this we know how to compute, minus p, we know how to compute, plus p squared. But what do we know about these people? We can say that we know how to compute him, and here we also will have p squared, so it will be p squared minus p squared minus p squared plus p squared, and this is just a 0, right? Okay, so now it's time to prove our main result for this piece of the lecture. So we will apply all these boring computations to make a conclusion about the asymptotic behavior of this random variable. So first we need a lemma, which is again a classical one from the point of view of probability, but for those who have not studied probability yet, I will make a self-contained proof and recall what is it. So this is a Chebyshev inequality, and it says the following thing, Chebyshev, sorry. It's the following thing, that if we take some non-negative random variable, and we know that it has finite mathematical expectation, then for t positive, we have that this probability can be estimated like this. Понятно, что тут написано? Или не очень разборчиво? Значит, мы взяли неотрицательную случайную величину с конечным мат-ожиданием, и тогда мы сказали, что для любого положительного числа вероятность того, что наша случайная величина не меньше, чем это положительное число, можно оценить как ее среднее значение, деленное на t. Окей? Значит, давайте убедимся, почему это так. So, since our random variable is non-negative, we can make the following computation. We can say that the probability that it is greater or equal than t is a sum under the condition that it's satisfied of the probabilities of every event that is like that. But then we can say that this can be estimated as the same thing over t, probability of our event, and we still sum up over all the events such that our random variable takes values that are greater or equal than t. Понятно, да, что мы сделали? Здесь мы написали просто по определению. Сказали, что эта вероятность, это как раз то же самое, что вероятность, сумма вероятности всех событий, когда это оказалось верным. Потом мы сказали, что раз это верно, то если мы тут разделим на t, то мы будем получать что-то, что больше или равно 1. Значит, тут мы просто помножили эту штуку на какой-то коэффициент, который больше или равен 1. Имеем право. Okay, so now we say that this can be seen as a 1 over t of the same sum. But then we can just get rid of this condition that makes our life so complicated and sum up over all possible events. So this is 1 over t of the mathematical expectation of our random variable just by its definition of the mathematical expectation. А мы все считаем в дискретном случае. Мы сейчас вообще не имеем дела ни с какими непрерывными случайными величинами. У нас все даже определения в начале курса были прямо ужасно дискретные, потому что, ну, как бы, на то мы и занимаемся цепями Маркова, а не марковскими процессами, чтобы себя не перетрудить в этом контексте. Great, so we proved Chebyshev inequality, and now it's just one line to extract this theorem from this inequality. Let's push for it. So we want to estimate this probability. Let's see. Probability that this nice random variable has a value which is greater or equal than epsilon. But it's a complement to the event we have here. And this looks almost exactly as we want in the Chebyshev inequality, right? Instead of t, we do have epsilon, and the random variable is the absolute value of something, but still it recalls a lot the Chebyshev inequality. So let's do it. We can say that this is nothing else than what? Than a probability that everything is multiplied by n, so this is greater or equal than n epsilon. So this will be something like var n square epsilon square, and we already made this computation. So we can say that this is a np 1 minus p n square epsilon square p 1 minus p n epsilon square. These are all constants, and so it goes to 0 when n goes to infinity. Я думаю, что нам хватило бы сейчас. Ну да. Мы написали сразу дисперсию просто, да. Ну, вы правы, да, можно было сделать еще полшага. Вот. Okay, Daniel is right, because indeed here we wrote the variation immediately, the variance, sorry, immediately, and not the mathematical expectations. Formally speaking, we use not the Chebyshev inequality itself, but the Markov inequality, but basically it's a direct corollary, so you can make the same extraction here in one line. Okay, so we proved the law of large numbers for this very particular case when we have an homogeneous sequence of independent trials. Now, we still have two more points of our cultural program today. Namely, I would like to prove you a law of large numbers for Markov chains with finite number of steps, because as you remember, the ergodic theorem we proved twice, basically. First time we proved it for any number of states, maybe not finite one, but we used the law of large numbers. So it's forbidden for us to mix up, because we could be in a logical cycle. And second, we did not use any law of large numbers, but we used Perron-Frobenius theory, so we assumed that there were matrices of finite size. So I will study the matrices of finite size, the Markov chains with a finite number of states, and then if we have enough time today, if not then next time, I prove you the law of large numbers, or at least explain in the full generality, and then we will be allowed to treat also Markov chains with infinite number of states as well. So let me switch to the law of large numbers for Markov chains with finite number of states. So, as in the previous case, we will introduce a similar random variable. It will be, this time, not the number of successes in our trials, but the number of occurrences of state number I. So, we will say that this is a number of occurrences of the state in sequence so we also introduce random variables with two indices, with double indexation. So it will be the number of those for which we fix two events. So we know that we were in state I at one moment, and at the next moment we enter the state J. Sorry. Значит, понятно, да, что мы действуем похоже на то, как мы действовали в своем игрушечном примере. Но теперь у нас исходов гораздо больше, хоть и конечное число, но их вовсе может быть не два. Поэтому мы будем заводить случайные величины с дополнительным индексом для каждого состояния. Это будет своя случайная величина, отвечающая за то, сколько раз мы в это состояние свалились в наших n-испытаниях. А это будет еще более хитрая величина, которая будет говорить, что мы должны были быть вначале в состоянии I, и в следующем шаге в состоянии J. И мы будем считать, сколько раз у нас вот таких комбинаций выпало. Okay, so what is the theorem? So let pi be the stationary distribution.
Чтобы оно попадало именно на то же самое место, то есть чтобы state I был, там, например, если оно равно омега четвертому, чтобы оно было вот последовательно на четвертом месте.
Не-не, мы считаем, сколько раз в этой последовательности мы вскочили в это состояние. Ну, то есть вы там прыгаете по классикам, там. Я вас считаю, сколько раз вы наступили на клетку номер 2. Это будет ν2 из ваших n прыжков. So this is a stationary distribution of an ergodic Markov chain. Then, for any positive epsilon, lim probability nu k n n minus pi for greater or equal than epsilon. This is equal to 0 for I between 1 and n. And this is probability nu ij n over n minus pi ej greater or equal than epsilon. So this probability is equal to 0 again. Значит, давайте разберемся, что мы тут написали. Мы взяли какую-то эргодическую цепь Маркова. Вы помните, что эргодические – это самые любимые наши. У них все хорошо, там неприводимость, апериодичность, там все при них. И у такой цепи непременно было ее стационарное распределение. Мы с вами доказывали в прошлых сериях. И тогда, что мы здесь доказываем? Мы говорим, что на самом деле вот это стационарное распределение будет, по сути, отвечать за предел того, как выглядит в среднем вероятности попадания в наше состояние. Здесь должно быть I.
Да, но I, наверное, вряд ли это n, нужно предел по n, как экран выглядит.
Не-не-не, сейчас мы сообразим. Так, предел у нас должен быть по... Нет, это тут n должно быть.
Тогда состояние должно быть не до n.
Сейчас, секунду, мы сообразим. Да, нет, вы правы. У вас испытаний должно быть. Тут до k. Вот. Наверное, так. Но мы сейчас сообразим. Когда мы начнем доказывать, мы проверим, где я вру.
Имейте в виду, что вы нигде не слабое состояние.
Да.
Вы нигде не реально просто путаете, потому что у нас двойное количество состояний и предел. Вот. Так, наверное, лучше как-то ограничить.
Okay, so let's see. Indeed, we have, you are right, because we have, n is here, it's the length of our trials. And here we want to distinguish these two ends. You're right. Okay, so let's see why it should be true and how we can prove something like that. So we consider так, давайте здесь поставим не k, а n большое, чтобы отличать, потому что k там у нас уже тоже поучаствовал, иначе мы завремся. Okay, so we consider the characteristic function as we like. So it's 1 when we entered the state I, and 0 when we did not enter the state I at the step k. So then we can also make double indices characteristic function. This is more demanding. It says that it is 1 only if we entered I on one step and j on another step and 0 otherwise. So then, as before, we take the sum of these people and we sum up from 0 to n, and we take the sum of these people. Здесь все точно как в предыдущем шаге, когда мы монетки бросали. Ничего нового. Просто считаем, сколько раз попали в тот исход, который нас интересует. И у нас два вида интересов. Попасть просто в свое родное состояние и попасть в это состояние, на следующем шаге еще в одно определенное состояние. И считаем, как часто мы приходим к успеху. So, for an initial distribution, I will denote it by nu. We can say that the mathematical expectation of the function, the characteristic function, is what? This function takes values as before, only 1 and 0. So this mathematical expectation in reality is nothing else but the probability of this event. But the probability we can compute if we know the initial distribution, we know the transition matrix, so we can compute any probability, right? So we can say that this is a sum of mu m p m I k. And in a similar way, we can do the same thing for our double index guy. We can say that this is a sum of mu m p m I k p I g. And here, indeed, as Daniel remarked, we have n already, capital N, not the n we used before. Окей, значит, ну это, наверное, понятно. Просто по определению того, что есть мат ожидания, у нас супер примитивная функция, она умеет только принимать значения 1 и 0. Поэтому мы дальше должны брать это самое распределение начальное, умножать на матрицу переходных вероятностей.
Большой, теперь что такое?
n большое, но это число состояний, мы же теперь считаем. Мы же просто умножаем по компонентам. So now we can see what happens, what interests us. We need to understand what happens when we go to infinity here, right? We want to know what about the limit. So what do we know? We know that from the ergodic theorem that we discussed last time in connection with Perron-Frobenius and before in more probabilistic sense, we know that there is this convergence, that the elements of the transition matrix, they converge to the components of the stationary distribution, right? And actually, in reality, we know that this convergence is exponentially fast. It also follows from our Perron-Frobenius theory, because exactly the Perron-Frobenius value was greater than 1, so the rate of this convergence was exponential. So we know this. But then, what does it mean for us? We can apply it to these formulas, and thus we can say that if we take k to infinity, then we will have k goes to infinity. So we have a convergence here, and we do have convergence here. And all these convergences are always exponentially fast. And this is a nice corollary of the ergodic theory. So what it gives us in reality, it gives us the statement that then we can compute the mathematical expectation of this person and of this person divided by the number of trials. So let's see how to do it. Then we can say that the mean of this guy is the mean of what? It's the sum of this xak divided by n, and we sum up from 0 to n. And what can we say about these guys? That okay, this series, it goes where? We know that all the members, right? They go to this stationary distribution part. So this should go to the stationary distribution. And in the same way, we do for the second person. Okay, so consequently, we can say that we have this type of convergences. So now we need to go to something like this. So we need to switch to something that looks like a law of large numbers. So it will require a bit more of work. Let's try to do it. So we say that for sufficiently large n, what can we say about the event that mu in omega divided by n minus pi is greater or equal than epsilon? This event is a part of another one, which is the event of mu in omega so is it clear what we did here? We considered this event. This is a complement to what we are interested in, right? So now we say that it can be seen as a part of the following person. The start looks as before, then pi we replace by 1 over n of the mean of nu in, and we want that this difference will be estimated by half of epsilon. Of course, this event is larger than this one, because this person goes to pi. So if the difference between them is larger than epsilon, it's a stronger requirement than the fact that this distance is greater than epsilon over 2. And in the same way, we can write the same thing for this guy with double indices. So let's see how to estimate these probabilities that we write on the right hand. Понятно, да, что происходит? Мы с вами убедились, что там есть сходимость, и теперь мы хотим понять, откуда возьмутся вот эти утверждения, как в законе больших чисел, которые мы уже успели доказать. Для этого мы действуем похожим образом, то есть мы рассматриваем не то событие, которое там написано, а дополнение к нему. Хотим оценить, когда это колебание большое. И говорим, что в силу того, что мы знаем, что на самом деле вот это вот среднее сходится к нашему PI, можно поместить вот это событие вот в такое и оценивать дальше вероятность вот такого. Понятно? Окей, so we say that the probability, this person can be estimated again from the Chebyshev inequality. Or maybe you are right to say from Markov inequality. So what we will say? We will say that the probability that this probability is like that. Epsilon square and square. And the same thing can be said about the second double indexed random variable. So this probability is nu EG minus mathematical expectation. And this is also estimated in terms of the variance of this. So now the only thing we need to do, due to the work of smart people like Chebyshev and Markov, is to estimate the variance of these random variables, right? Before, we just made computations, so we knew the precise values of these things in the previous baby example. Here, we were not given them for free, but we can try to make this estimation, and we will use ergodic theorem again to do it. So let's see how it will work. So we make more notations. Mu S, P, S, I, K. So what is this variance? It's a mathematical expectation just by definition, you remember. We consider it as a difference between the random variable and its mean in square. So that's what we need to compute. So let's do it. What is it? This is a mathematical expectation of this sum. Xik Mik square plus k smaller than k2 Окей? Ничего криминального, просто мы расписали все по определению, примерно так, как мы делали, когда в прошлый раз вычисляли, собственно, саму эту нашу дисперсию. So what can we say about the first guy? I claim that it is smaller or equal than 1. Each of the elements here of the random variable, it's smaller or equal than 1. Do you agree that it should be true? Because what is this? It's a characteristic function, so it does not take values except 0 and 1. At the same time, of course, the mean, which is the mathematical expectation of some characteristic function, it also cannot take values between 0 and 1. So if we consider their difference, we can be between -1 and 1. So when we take a square, we go between 0 and 1. And we don't want more, because I can conclude that all this sum can be estimated by n plus 1. Because we have n plus 1 elements, each of them is not larger than 1, right? Not greater than 1, so we have. Okay, now our favorite part. Before we were very happy to show that it was equal to 0. Today, here it will not be 0, and all our work will be basically concentrated on the estimation of this person. So. I will write and then comment, just because it's very boring. So what I'm writing is simply that we try to make this computation. What can we say? We will have some product of them. We will have MI K1, M2 K1. And we know also mathematical expectation of each of them, that it's equal to mi. It's just our notation. So when we compute all of them, we will have this product that we don't know how to estimate. And then here we will have what? It will be mi, mathematical expectation of he k2, so it will be mi k2, and the same here. So we sum it up. There will be then 2 guys with minus and 1 guy with plus, so it will result in this person, right? So that's what we get. And then we can say that we know how to calculate it, because it's what? It's a sum mu s psi k1 pii k2 minus k1 minus mi k1 mi k2. And this crocodile will be denoted by r k1 k2. And now we can try to again use our ergodic theory. How exactly we want to use it? We know that the rate of convergence in ergodic theorem is exponential. So in reality, we know more than the fact that it converges. We know that the distance between mu0 Pn and our stationary distribution is the distance between mu0 Pn pi Pn. So you estimate and estimate, and every time you can extract 1 minus alpha m mu0 Pn minus ms Pn minus ms. And so you can say that all these can be estimated by some number in the power m, where alpha is a Perron-Frobenius number of the corresponding matrix. Да, мы пользуемся тем, что у нас сходимость в эргодической теореме не просто была, а она была экспоненциальной. Помните, мы в конце, значит, когда мы доказывали эту теорему Перрон-Фробениус, дальше мы могли оценить, пользуясь ею, вот это вот. Ну, то есть здесь у нас что написано? Это же собственный вектор нашей матрицы. Поэтому мы хотим, по сути, мы доказываем, что тут мы умножаем на произвольный вектор, тут мы смотрим на наш вектор Перрон-Фробениус, все, предел к нему сойдется, и сходиться будет со скоростью, за которую отвечает коэффициент Перрона-Фробениуса там, в n-той степени. Значит, мы можем это оценить таким образом. So what is m? M is such that n minus ms is smaller than s, but positive. So, in other words, we can say that there is no doubt that the distance between these 2 points is 1 minus alpha minus 1 bn, where beta is 1 minus alpha over 1 and s. It's smaller than 1. So now, how can we apply this remark? So this is just a direct corollary of the ergodic theorem. So how can we apply it to estimate this R k1, k2? We can notice that we can write up mik as pi plus something. And this something can be estimated as some constant on lambda power k. And the same way, we can say that this psik is pi plus something, which is beta sik. And again, this beta sik is something very small. It decreases exponentially. So the sum we are interested in comes from the following statement. It can be seen as a mu s pi plus b si k1 pi plus b ii k2 minus k1 minus pi plus di k1 pi plus di k2. So all these things just result in the fact that we have some unclear constant lambda k1 plus lambda k2 plus lambda k2 minus k1. If C1 is negative, is finite. So we can compute that if we need to sum up these R's, it can be estimated as some constant multiplied by n. And so finally, we know that all this variance we have here, right? What is it? We know that it was like n plus 1, and we know that here it was also something very linear. And so everything like that could be estimated in a similar, so all these guys, it's just some C3 on M, right? So it's a linear estimation. And the same would be true if we consider double index here, and that will be enough for us, because as you remember, I already erased, of course, but we had m square in the denominator, and we have something linear in numerator. So let me repeat the general logic, because it was very technical and boring for you, so probably you're already lost. The general logic is as follows. We start with the logic similar to what we did in our baby example. And we try to make some computations to replace this thing by something that is easier for us to treat. Already at this moment, we apply ergodic theorem to replace sometimes our elements of the high power of the transition matrix by the values, the components of the stationary distribution. Then we try to make the computations to apply Chebyshev inequality and Markov inequality. And so we finish at the point when we need to compute the variance of this person and of the similar person, but with two indices. The difference of the general case with respect to the baby example is that in this case we cannot make the precise computation because we know too little about our Markov chain. But we still can make some estimations. So the first half is very evident how to estimate it. It was very easy. We just used the fact that our random variable, and of course its mean, that well could not exceed 1 in its absolute value. So we concluded that then each element of this sum does not exceed 1, so the whole sum does not exceed the number of summable elements. But then there was this crocodile, and it was much harder. But thanks God, we know what ergodic theorem states, and ergodic theorem told us not only about the fact of convergence, but also about the rate of this convergence. So we knew how to estimate the difference between our stationary distribution component and the element of the corresponding matrix. So by this knowledge, we always could write things like that, and we knew how to estimate these additions. And these additions were negligible with respect to the main parts, so we could be able to make this computation. Pi would die at this moment, and we would need only to deal with the rest. So the rest contributed by something linear, and it was a difference between two linear functions, so we could be sure that it's at most linear function. So then, as you remember, in this Markov and Chebyshev inequalities, we had to divide on n square, while as the denominator we had something with asymptotics given by n itself. So then we got something that goes to 0, and so the complement will have the value we want with the probability 1. And okay, so I hope it was relatively understandable. And we still do have some time to discuss a little bit the law of large numbers in the full generality, not for Markov chains, but also not for these particular random variables that we started with. So let's try to do that. So we consider a sequence of random variables. We assume that they have a finite mean. And we say that this sequence satisfies the law of large numbers if zeta n minus zeta n averaged converges to 0 in probability. So it means that the probability that these guys have difference that exceeds epsilon goes to 0 when n goes to infinity for any epsilon. This is a definition when they satisfy the law of large numbers. There is also a law of strong law of large numbers. So strong law of large numbers it's when we require more than that, more than convergence in probability, when we require convergence almost surely. What does it mean? It means that this limit for almost all omega. So it's very easy to extract the law of large numbers, not the strong one, the standard one, in case when our variables are independent and the variance is finite. So you can just apply the Chebyshev inequality and say again as we did before, basically. So how do we proceed? We say that the random variables are independent and var is finite. Then we apply these inequalities and we say that the probability that we have the difference which is greater than epsilon, it is what? It's nothing else than the probability that the sum of these people minus sum of their mean is greater or equal than epsilon n. And this can be estimated in terms of the variance of epsilon n squared. So this is some constant on epsilon square n. So it should go to 0. Right? Clear? Значит, если у нас есть сведения про то, что наши случайные величины независимы и у нас конечная дисперсия, тогда можно просто применить то, чем мы уже здорово научились пользоваться, и у нас сразу все будет получаться. Но в общем случае так лихо не выйдет, и придется еще немножко поработать. Значит, я сейчас сформулирую теорему, я не буду ее доказывать, но это просто для общего развития. Это закон Хинчина, закон больших чисел в форме Хинчина. А доказывать мы будем в форме Колмогорова. Это просто для общего развития. Любители динамических систем потом смогут вывести это из эргодической теоремы Бергофа. So a sequence, say n, of independent, identically distributed random variables with finite mathematical expectation satisfies the law of large numbers. Обратите внимание, что здесь мы уже не требуем, чтобы у них была конечная дисперсия, но утверждаем, что на самом деле нам все равно достаточно конечного мата ожидания. На самом деле верно больше, и вот это больше, которое верно, это теорема Колмогорова, которая утверждает, что это закон больших чисел в форме Колмогорова, который утверждает, что у нас будет выполняться даже сильный закон больших чисел. Но это мы, наверное, обсудим с вами уже в следующий раз, потому что я не успею сейчас доказать, вот, чтобы как-то это было более-менее монолитно. Ну и вернемся к нашим любимым цепям Маркова. Будем их домучивать. Я напоминаю, что у вас есть листочек. Я сегодня напомню учебному ассистенту, что на него в выходной обрушится лавина его решений. И вот, как обычно, он будет его проверять там сколько-то, наверное, неделю. После этого мы сделаем табличку и назначим, когда вы мне что-нибудь расскажете про решение. Thank you very much for your attention. See you next week. Thank you.